And Jonathan, you can
Yeah,
do you.
we're joined by Max Di Luca. He performs both fundamental and applied research to investigate how humans process multisensory stimuli, with emphasis on understanding the temporal, dynamic, and interactive nature of perception. He's been a Turing Fellow and a Fellow of the Intercontinental Academia. He's worked as a scientist at the Max Planck Institute for Biological Cybernetics and as a research scientist at Facebook Reality Labs. And he currently serves as an associate professor at the University of Birmingham in the Center for Computational Neuroscience and Cognitive Robotics. I'm a big fan of some of his work, and I'm really excited to hear him speak. So welcome, Max.
Thank you, and thank you for organizing this event and the series, and for the work you put into this. Thank you, everybody. I see that there are several participants online. Yes, if you have questions that you want to ask me at the end, that would be great. But if something is unclear, please raise your hand. I hope that I can see it and stop and clarify what, or maybe write me a question in the chat and I'll clarify what is there. I haven't given a talk on timing for like a long talk on timing for a while because, as you said, Jonathan, I've been working with the industry, and so my career path has had a little swerve. So I've been working a lot recently in augmented reality and artificial intelligence. So I thank you not only for the opportunity to give this talk, but also for making me go through the things. And whenever you give a talk, you think about the ideas and kind of I got excited again about the topic, and I wanted to do it more. But as you can see, so these are the papers that I want to refer to in this talk. There are several ones that are in 2016 when I left for Facebook, and only a couple of them that are more recent. And I refer to this ARME project, which I'll talk about it towards the end for more information and for some of the tools and data sets that are available. I want to start with a very simple example, so to set with the context of what I'm going to present. The example is, imagine you are clapping your hands, right? And or you hear a clap, and you hear a kind of a regular number of sounds. And so once these sounds have given enough information, so as there are more and more sounds, you kind of start to have an expectation of when the next clap is going to appear, you're going to hear it. And if it happens that this clap is not at the right time, you would certainly be able to hear it, right? We have the impression that if we hear a clap and then one is a little bit earlier, a little bit late, we would definitely be able to detect it. And this is basically what the experiments are going to present will be about. So a series of quasi-regular sounds, and then a final one that is can be a bit off. So in one of the kind of tasks that you can ask participants to perform is to tell whether the last clap that they hear in a sequence is either late or early. And now I'm going to present a couple of experiments we have done to try to capture, how good we are to tell whether the last stimulus is early or late, and whether there are perceptual distortion in this process or not. So the task is early, late, but the number of stimuli you have could vary. So you could have like 3 stimuli, and it could be, you see, the last stimulus could be either presented early or late. And if we do a psychophysics kind of experiment, so we have different asynchronous, and we ask multiple times the participant to report. And out of this data, we have a psychometric function that looks sort of like that. If we plot the proportion of late responses, so the vertical line is the physical isochrony, so where the intervals are equivalent, and you can see that the psychometric function here is a little bit shifted and is not all or nothing, but there is a slope. And those are the parameters that we will look in a second. But you know, there are not only 3 stimuli, you could have 4, 5, or 6 stimuli. Now, one of the first questions we had at the time when we started this project was, how does the precision change depending on the number of stimuli? So if we look at a sequence of 3 stimuli and we modulate the duration of the last stimulus, so we have the base interval of 700 that we can add or subtract up to 200 milliseconds of asynchrony. And we get this kind of proportional responses that is like this for 3 stimuli. If we go with a sequence of 4, we'll have a sequence psychometric function that is like that, and etc. if we go 5 and 6. You might notice that there is a slight increase in the slope and maybe not so much change in the kind of the point of subjective equality, which is the 50%. And if anything, there is a slight change towards the positive side. Okay, so we can determine the point of subjective equality is 50% and the slope as the J&D. I hope that you are familiar. If not, I can explain it a little bit more in detail. But so if I were to plot the point of subjective equality and the J&D for these 4 kind of duration, so with 3 stimuli, we have a J&D of like about 100 milliseconds, and then you can see that there is a slight decrease in J&D as the sequence is longer. In terms of the top graph is presented interleaved, so all this duration, you don't know which one is presented. On the bottom, you can see that we have done the same presentation, but the duration that you have been presented are blocked. And you might notice that the performance increases a bit because all the values are of J&D are about 80 milliseconds. You can see this is summarized on the right. The blocked presentation of duration is definitely better. So we have this data, and it's psychophysics is nice, but like what I'm interested in general is to try to have a quantification of performance. And so we looked in the literature what kind of models are there that can allow us to make a prediction about the performance, for example, the performance increase that there is in J&D with different durations. And so at the time, we have found these different models, and I go through 4 of them. One is called the perceptual average by Schulze. So basically, it postulates that when comparing a duration, like the duration of the first n interval to the last one, the perceptual system makes an average of all durations. By making an average of all duration, basically the average improves the reliability, the precision of the estimate. The downside is, and I try to represent it here graphically with this vertical line, is that when a sound is presented in a sequence, it could be affecting the precision, the timing of this sound could belong to the previous stimulus and to the next. So when there is a duration estimate, the sound that is in between the 2 durations, if there is a mistake, the mistake is correlated, right? So if you misunderstand the exact time point of a stimulus and it's too late, it will affect the next interval because it's too short, but also the previous interval because it's too long, and vice versa. So there is this kind of correlation, and this is a hidden parameter of this model. So the more correlation there is, you can work out the math and show that the less improvement in performance there is. Another very similar model is the multiple look. So the idea here by Drake Botta is you look multiple times when you have a sequence at each interval, and each interval can have a different amount of information. So you can kind of weight the amount of information for each interval. And here I try to represent it with this different thickness of the line. So, you know, one interval could be very heavily weighted and another interval less, and etc. So it's the model is a little bit more free in assigning the weight in the evaluation. So depending on what kind of weight you use, you could have like an equal weight to all the intervals. So you know, basically you're doing an average and you're an optimal integration of duration. Similar model that does an average, but keeps an internal reference of one of the interval, and basically in a way similar to a Kalman filter, it takes an average, so the memory storage is only of one interval, and as a new interval comes in, this model makes an average with the new one, and then just stores the last interval. So for very long sequences, the memory allocation is very efficient because you have only one interval. But the problem is that you need to, when you're doing an average, you need to kind of weight how much importance you give to your memory and how much to the external information. And this is the parameter that is allocated by this model. Finally, the diminishing return says that as the sequence goes on, simply the amount of information that is provided by each interval diminishes in importance. So it's a similar approach that the multiple look, if you want, but it's more constrained in terms of the amount of information always decreases over time. So I kind of explained them very quickly, but if you go on the paper, you can find all the maths that describe the exact prediction of performance of each of these models. And in fact, what we can do is we can look at the number of stimuli on the x-axis and then the predicted J&D by this model. So given that there is a performance with 3 stimuli, we can make the prediction for 4, 5, 6, 7 stimuli, or even 1,000 stimuli for that matter. And we can do this with each of the 4 models. So, for example, for the perceptual average, we'll have this kind of performance, and depending on R, which is a correlation between the 2 successive duration in 2 successive intervals, you would have different kind of patterns. So if there is no correlation, for example, that would be the line in the middle. You would assume that that's the best performance, but it turns out that if there is anti-correlation, so the correlation is negative, you would go and improve even more the performance as the effect as the sequence becomes longer. Another model, the multiple look, shows here that if the weight, as the weight changes, there are also different kind of improvements. You might notice again that there is a dotted line in this graph, which represent a weight of 0.5, which is correspond exactly to the performance that you would predict with the perceptual averaging model. In fact, the two are they have a very similar expression. You can see that if the weight changes, the performance increases or decreases differently. So with a weight of 1, the performance stays always the same because you basically give a maximum weight to the last interval in the sequence. But if you go and decrease the weight, and so assign an equal weight to all the stimuli you have this paradoxical point here where the J&D basically becomes 0. So with infinite sequences, you would have infinite precision. Another model, an internal reference, as I said, constitute the an internal averaging with a reference, and averages basically iteratively with each subsequent interval. And so here the performance doesn't improve as much as with the other models. And finally, we have the diminishing return model that has a wider range of possibilities. So these lines, they are very, very far. They can also increase above the JND that is with 3 stimuli. So performance can actually decrease with along the sequences. So the shape of this pattern is a little bit different. So we can take the data that we have collected in the experiment and try to fit it. And this is what we are trying to do here. So the line, the full line is the different models, and the dotted line is the JND that we obtain with the participants. And so this is the best fitting pattern. And you can see that for the perceptual average, the multiple look, and the internal reference, we have a very close fit, while for the diminishing return, the pattern really doesn't fit. In fact, we have plotted here the sum of errors. So lower value here indicate a better fit of the model. And we can see that the perceptual average and ML, they are the best fit, while instead the models on the right have worse fit. So what have we learned here? Well, we have learned that an optimal, statistically optimal model can predict very closely the performance of the participant in terms of precision of determining whether the last interval, the last stimulus, is too early or too late. But when we look at the data as a whole, we have not really looked at the PSC. So we talked about precision, but there is also a pattern of PSC. And if you say that if participants were optimal and everything was perfect, those PSC should really be 0, right? So there shouldn't be a bias. But in fact, we found a bias, and the bias changes depending especially on the interleaved and blocked presentation. So we wonder whether it's the kind of the stimulus or whether it's the kind of task that we have used. And to assess that, we have asked the participant to perform a slightly different task. We asked them whether the sequence of stimuli is perceived to be irregular or regular. So again, if the last stimulus out of 3 in this case is early, or if it's late, the participants would say that it's irregular, and whether instead is towards the middle, they would say that it is regular. So this is the kind of psychometric function we would expect. And again, we have tested this with different length of the stimulus, different duration of the sequence, right? So something is not working. Okay, so this is the kind of data we will look at with 3 sequences. We have a pattern of response that looks like this. For the kind of the psychometric function looks a bit more shrink, and 5 and 6. So you can see that the psychometric function is shrunk. So there is more conservative criterion, so saying that the sequence is regular. It's more conservative, so there are less regular or isochronous responses. But it's also evident that this effect is mostly on the negative anisotropy. So for stimuli that happen earlier than expected, there is a change depending on the sequence length. So we can see also this in this way. So if we plot the 50 millisecond, you will see that the intersection with the psychometric function is also symmetric. Okay. Here we have done something slightly different, but not really. So here, because we have in the next experiment, we have lights as well. So we have asked the participant to not only judge isochrony sequence of sounds, but also of lights. And the pattern is very similar in terms of, there is this kind of Gaussian, but it's asymmetric depending on the duration. So there is a change in the proportion of responses, especially for negative asynchronous, which are stimuli that are presented to you might wonder why the function here is flatter. Is because it's more difficult to tell whether tell timing of visual stimuli rather than auditory one. Okay, so again, we have this kind of misplacement of the perfect asynchrony. So participants tend to have a bias in the responses that they produce, and we want to see it in more detail. This is a way that we have found to try to measure whether there is a distortion in the perceived timing of the last stimulus. So with a sequence of 4 stimuli, what we have done, we have presented the 4 stimuli auditory, but we have also associated a light with the last stimulus. In this way, the participant has only to perform a temporal order judgment task, so tell whether the last sound in the sequence is presented earlier or later than the light. So now we don't ask anything about the sequence itself, but just about the last stimulus. Why we are doing this is because we can determine with a psychometric function, right? We present the flash earlier or later, and we can determine whether the perceived timing of the auditory stimuli has been distorted by the preceding sequence of sounds. So if we would find that the point of subjective quality in this psychometric function is matched with the point of objective quality, then the previous sequence does not have any influence. But we expect there to be some distortion. So let's look at what kind of distortion there could be. So for example, if we have this sequence here, so the sounds are regular and then the last stimulus is presented too early, we would expect, or in this case, like we would have sounds presented regularly and then the last stimulus presented too late. What are our expectations? So if it's the sound is presented too late, we would expect the previous sequence to kind of capture this stimulus and shift it perceptually in time earlier. Okay, while if instead is presented to the last stimulus is presented too early, we would expect the perceptual stimulus to be shifted to appear late. And so this is identified here on the psychometric function in this way with these 2 colors on the right. Now, we could also ask the participants to judge the temporal order judgment of the sound and the light when the previous stimuli are actually lights. So depending on whether the last light is presented earlier or later comparing to the previous stimulus sequence, you might expect a kind of a distortion, perceptual distortion of the timing of the light. So to balance this, the experiment we have done with sequences of light and sound, so the participant doesn't effectively need to pay attention to what is presented before the 4th stimulus here. They just need to evaluate the sound and the light, the temporal order. Okay, so how I will present the data is like this. So on the x-axis, I will present the anisochrony of the last stimulus compared to the sequence that precedes it. And on the y-axis, the point of subjective simultaneity. So it's the asynchrony at which the sound and the light should be presented for them to be perceived maximally in a chance level, effectively. So it's kind of like they are perceived mostly simultaneous. Okay, so it is renowned that the PSS of the sound and the light is about 30 milliseconds. So you have to present the light slightly earlier than the sound, because the process of the light takes more time than the sound. So I represented this here. On the diagonal here is a prediction of whether the participant would actually ignore the last stimulus and follow just the sequence and use the sequence to predict when the last stimulus will be presented, and then use this prediction to answer whether it is earlier or later than the stimulus in the other modality. What we expect is something in between. So with the sound sequence, we have some sort of pulling if we go on one side. So the previous sequence distorts the time of the last stimulus. And if I look at the other side, so when the stimulus is presented later, there is a slight distortion, but then with the asynchrony at 80 milliseconds or too late, there is no distortion. What happens when we have a sequence of light? Well, the pattern is now reversed. So it's kind of symmetrical, just around the 30 milliseconds. So in this way, on the negative side of this anisochrony, when the stimulus is presented too early, there is a pull to postpone, and the kind of reverse pattern as the sound is present. Okay. So here there is basically when the sound is presented or the light is presented later, there is an acceleration. And on this part, when the sound or the light is presented too early, there is a kind of perceptual delay. Okay, so how do we explain this? So here is when I take in my, my preference for Bayesian models. So I described before several kind of models, but here I will present kind of a probabilistic inference kind of model. So the general idea is that there is, so this is one graph that represents a property in the word X and an observable property R. And your task as a participant is to infer X from R. So infer what the state of the word is based on your senses. And one of the formula that is being used to help us in this task is the Bayes formula, which says that the probability of the X in the word given the R, which is the stimulus, can be expressed in this way. It can be split into the probability of the R given the stimulus, which is the generative process. So it's called the likelihood of the stimulus, and Px, which is the a priori expectation. So this is a kind of a mathematical formulation of it. The factor that is at the bottom is usually kind of forgotten. Is kind of just a normalizing factor. So this the three terms that we are focusing on are called the likelihood. So this is the probability associated with the stimulus, the prior, which is the probability associated with the expectation of the stimulus, and then the posterior, which is the actual kind of inference that is being made about the word out there. Okay, so how can we use this in a sequence? So this has been used multiple times for in perception and cognition, but what about the stimulus sequence? So my observation was this, like in the clapping sequence, when there are two claps, if I make some assumption, I can kind of expect when the next stimulus is going to be. And I can draw here, because I know that now this expectation is called a prior. I can say that the probability of the next stimulus to appear will increase when the duration is projected in the future, right? And if this stimulus is now confirmed, then I can do the same kind of prediction and say, well, the prior for the next stimulus is going to be also the same duration, just more sharp, and so forth. Okay, so in terms of prior, I can say that the prior kind of increase in sharpness as the sequence increases if I make a lot of kind of assumptions about the process. what can we do with that? Well, if every stimulus is associated with this likelihood, and there is a prior there, for the first stimulus in the sequence, well, the prior is flat. I don't know when a stimulus will be presented, right? So I just can only use the likelihood. If the stimulus appears, right, and there is a second stimulus, well, I kind of, based on my expectation of how far away stimuli are, I can tell, well, there is maybe an average interval that I would expect. People say 0.5 seconds or 1.2, right? But there could be a little bit of shape there, but I don't want to make strong claims about it. But once the second stimulus appears, I can definitely make a prediction about the third one. I know that if stimuli appear regularly, then the third one should be when the same duration has passed. Okay, so if I go on like this, at a certain point, this prediction increases over time, and when I try to create a representation of my posterior, my perception, I can say basically that the precision of the timing estimate increases with the sequence as the sequence develops. For the last stimulus, which is the one that we are concerned about, we can make a little bit more refined prediction. So what happens if the stimulus is slightly delayed compared to the expectation? Well, if the stimulus is delayed, then the likelihood is not at the expected time point, but is associated with the stimulus, so it is also delayed. What about the prior? No, the prior is when the stimulus was expected. And so what happens to the posterior? Well, the posterior is the joint probability distribution between the two. So it's somehow in between the two, likelihood and prior. In fact, we can make a more accurate prediction and say that the center of the posterior is a weighted average between the prior and the likelihood, weighted by the reliability of the two Gaussians. If this were Gaussian, in fact, I'm trying to claim that these processes are not entirely Gaussian, but there is an asymmetry. But for the time being, we can say that the posterior is in between the location of the prior and of the likelihood. The more the prior is steep, the more the posterior approaches the prior. Okay. Why do I keep on saying that the shape of the prior and the shape of the likelihood should not be Gaussian? My intuition is that as we accumulate information from a stimulus, this could be taught as a Gaussian process or as accumulation of information. So basically, if you have a stimulus, you are trying to decide whether you heard the stimulus or not. And the longer the stimulus is, the more evidence you have that the stimulus has happened. So, you can say that there is a Gaussian process there with a noise parameter and accumulation of information. So if you plot the kind of distribution of probability over time, you would have this kind of function. And if you look at how what is the probability of hitting this decision boundary that you actually have perceived the stimulus, you would have a function that looks like this. I didn't invent this at all. A lot of people have made similar claims. But the point here is that, if this is your likelihood, then also your prior, this is the likelihood for light, the likelihood for sound on the left and for light on the right. So the sounds are more precise. There is a faster accumulation of information than with light, and that will give a faster response and a more precise one too. Okay, so this is the likelihood. What about the prior? Well, because the priors are actually based on the likelihood, so they should have a very similar function. In fact, the function that you show here is what happens if you multiply or point multiply the two likelihoods or three likelihoods. So they just shape up, they become steeper, and they maintain their mode. So their delay is the same, just the shape of their function changes. And you might notice that the tail on the right is shrinks as time passes, but the tail on the left does not shrink as much. What does it mean? Well, it means that even with multiple stimuli, you are able to slightly accelerate, but not so much. But the effect is on delayed perception. So you have a tendency of accelerating perception that is happening too late with multiple stimuli. Okay, and so the point here is that the likelihood is what generates the priors, and so the shape of the priors is very similar. Okay, so this is a simulation of what happens in a sequence using this kind of function. So again, we have a sequence of 4 stimuli. First, there is the likelihood, and the prior is flat, and the posterior is basically the multiplication of those. If you have the second stimuli, the prior is the same, so the posterior is exactly the same. Third stimulus, there is now a kind of blip that is basically the prediction of the next stimulus based on the duration of the first interval, and you can see that this little red bump actually affects the posterior, changes the sharpness of the posterior. So with this added expectation, now perception becomes sharper. And this is what happens when you present the 4th stimulus, and it could be a little bit earlier or a little bit late. And you can see that if the stimulus is presented earlier, then there is a big shift of the function of the posterior towards expectation, while if the stimulus is presented too late, the shift is not as big. So perceptually, we are able to delay the perceived timing of a stimulus, but not so much to anticipate it. So this is again a little bit more in larger with the larger view for both sounds on the left and lights. So the simulation basically tells us that if we take the data here with the temporal order judgment, the delay and anticipation, if we do the fitting with there is only one free parameter, basically we obtained this pattern of responses where there is a pattern of acceleration and a pattern of delay. Okay, so very close pattern of responses that we expect with the two models. This is with the parameter, so this is the parameter that we fit, so the shape of the function. Okay, so I'm speaking for 40 minutes. Should I? How are we doing with the timing? Do I have a little bit time more, or should I take a pause, or do you have questions so far?
Yes, we do have a few more minutes. So if you have more slides, please go ahead, and we will take questions for 15 minutes approximately at the end.
Okay. So we've tried to see whether this model works for other things. We've tried to look whether if the prediction is based on the single sequence, or whether different if there are multiple base intervals, whether the prediction carries over from one sequence to the other. We've seen that we have done this by interleaving different base interval. We still find an effect. So basically, there is a little bit of carryover, but not a large one. We have tried to look at whether the regularity of the environment has an effect. So in this experiment, we have asked, we've split the participant in 2 groups. In one group, for 75% of the stimuli, the sequence was regular, and only so there was like very small jitters, and 25% of the sequences were perfectly regular. While for another for another group, we have given a large amount of jitter for 75% of the stimuli, and 25% were still regular. So basically, if the perceptual system kind of captures the regularity across stimuli, right, and uses this regularity, this high-level regularity, then does it transport it to the 25%? We have used, again, the temporal order judgment pattern. Basically, we find that if we look at the zero as an isochrony in the sequence, which is the same 25% of stimuli, they are perfectly regular. If they are embedded with a context of regularity, then there is a perceptual distortion due on the previous stimulus. But if they are if these 25% stimuli are embedded in an irregular sequence context, then there is no effect of the previous sequence. We have tried to look at other stimulus property. We have looked at whether the predictability of the stimulus can have an influence. So we have changed the last stimulus. So the question was always on the regularity of the sequence, but we have changed. We could have regular scale or random sequences, and we have found that with random sequences, participants have a higher J&D, so they are worse in performing, and the pattern basically increases in performance with scales, not with random values. We also, so this is basically tells us that there is a prediction both for the tone and for the timing, but because the task that we asked the participant is about the timing, the predictability of the tone helps in the case of a scale. The last experiment that we have tried, and this is unpublished, we have changed the intensity of stimuli. So our expectation, if this stimulus is very strong in intensity, the likelihood will be stronger and sharper, whereas if it will be weaker, the prior will have a larger effect. So we have created different kind of sequences. So it could be regular or irregular, and the last stimulus could be strong or weak. So we have used this pattern to kind of measure whether there is acceleration and delay, and we find that the acceleration and delay is present as previously. So if the stimulus is presented too late, there is acceleration. If the stimulus is presented too early, then there is delay. But the point of this experiment shows that if the last stimulus is low in amplitude, then there is a much higher effect of the sequence, whereas if the last stimulus had high amplitude, the effect of the asynchrony is much smaller. We have created a model that tries to account for this as well, where basically when there is an interval between two stimuli, creates a likelihood in terms of duration. So we have explored kind of interaction between time point and perceived duration. And we have this model where the duration is projected to the next interval. So trying to summarize it here. So we have a time point estimate from a stimulus and a second time point estimate from the next stimulus, and the two they interacting, creating the duration estimate. And the duration estimate is projected in the future based on the timing of the last stimulus. And this is the low resolution, but this is the prediction that it makes. So here the effect size for each of the four conditions where we have either low amplitude on the left or high amplitude on the right. So more effect because the kind of influence of the sequence is higher for low amplitude and less effect to the right. You might see that there is an inconsistent sequence. It changes a bit the prediction because based on whether the previous stimulus was strong or weak, has an effect on the prior, and the model captures that as well. Okay. The last thing I want to mention is we have used the same kind of model to try to capture how people synchronize to a metronome. Usually, it's one of the model is the linear phase correction model. So the error is projected in the future, and there is a correction of a proportion of the error that is made. This has been used in music, and we have kind of, so that was the kind of reactive component, but we want to be able to have also the predictive component, synchronization, where the kind of expectation determines when the next stimulus should appear for influence performance. This is in the context of the ARMY project that tries to capture musicians, how they interact, and reproduce them in augmented reality. So we have a system where virtual musicians play with a real musician, and this can be used as a tool for music learning and music rehearsal. But in terms of scientific understanding, we have created this tool, which is called the adaptive metronome. And basically, there are multiple virtual tapper or virtual musician that synchronize to a real one. You can download this tool. It can be used with the Logic Pro and other DAW. I just want to present one example where we used it. So here we have a group of 4 virtual musicians. The experimenter, gives the headphones to the participant, and the participant needs to tap on a device. And as they tap, they hear a musical piece. Now the virtual musicians, they can synchronize or not synchronize to the music that the participant is producing. And we find that basically the more they synchronize to the music that the participant is producing, the less the participant is responding and synchronizing to them. Okay, so summary. Basically, I show that there is a temporal expectation that can improve performance in temporal judgment. Their perceiving timing is changed due to this expectation, and the expectation can be seen as a prior in a Bayesian model. So they serve a kind of a template, they modify perception, and action can be based upon them for correcting. The likelihood probabilities can be seen as an accumulation of information. Therefore, these likelihood probability are not Gaussian, and they shape the prior. This is why there is an asymmetry in perceptual effect. I have some data that shows that this model can be used to explain the effect of context. So whether the context is isochronous or regular, whether there are higher order regularities, whether the stimulus is predictable, and that the time point and duration estimates are interacting with each other, and there is a recurrent estimation of time and duration that is interleaved. And this model can be used for synchronization and error prediction, error correction and prediction. I would like to thank Susan and Darren that the data are basically mostly them, but also the augmented reality music ensemble team that has contributed to the tapping. And these are the papers I talked about. And so if you have any question, I'll be happy to answer.
Thank you so much, Max. I really enjoyed that, getting to see all of these things under the same umbrella put all together. I will open the floor for any questions. And you can ask by raising your hand or ask in the chat. Either is fine. Well, I've got quite a few if I want to start us out. I think first one is so it seems like you're interested in this for actual musicians. How do you bring these ideas to complex rhythms?
Yeah, it's good question. So the idea of having like time point and duration is only basically 2 levels, right? So we are thinking about higher level priors. So if you think, 2 durations, they could have a higher level prior about the change in duration and so forth. So you could have priors of different order. And so you have Nori Jacobi has shown, for example, a rhythm, right? So you have rhythmic priors where, based on the different duration, you have different probabilities. So that what Nori's three probabilities would be essentially a prior, a hyper prior in rhythmic space, and then you would have your likelihood based on the duration of intermediate intervals, and then they would have the prediction based on the next prior. So yeah, so it can be built in higher level. Would be nice to do it. It becomes complicated to test, but I'd be happy to if anybody wants to do some collaboration and try it out. I'll be happy. There is a lot of data that needs to be collected, like in Nori's experiments. Does it make sense? This kind of hierarchical prior likelihood, Jonathan?
I mean, I'd love to see the actual details, but we can do that later. Yeah, I've got more. One question is, you've got this temporal order judgment task. Do you think it would work within the same modality? I'm sure you deliberately did it in different modalities, but
yes, yeah. So the idea of having the stimuli in different modality there was to try to minimize the influence of the sequence on the matching stimulus. In fact, we have done a control experiment that I don't think made it to the paper, but I think it might go to a different one, where we have a sequence of sounds and then a light to see how much influence there is. And in fact, there is a cost of switching modality, and it's quite humongous. So now we could measure how much of this cost of switch modality is, and the point is, yeah, we could affect more one modality, like within modality, more than across. I think the risk of having the same modality would, you would distort the timing of both stimuli, and so have a smaller effect that you measure, and you don't know how much you're not measuring, really.
Yeah, I guess if you to minimize that, I guess you could put one very high pitched and one very low pitched or something like that. But I see, yeah, I see the problem.
Yes, you could do that. Probably the kind of binding will be less than if you do it multisensory, but yeah, it can be done.
Great. And because you guys are leaving all the space for me, I have yet more questions. Maybe I should stop and see if anybody else has anything to ask. But if not, I've got an interrelated pair of questions. One of them is, how do you think this uncertainty about when the next thing is going to happen might be represented in the brain? And then the related question is, how do you think this prior on when the stimulus would happen is projected forward in time over I mean, obviously all this has to take place in continuous time. So are there timers? Are there representations of specific distributions and tails? Can you comment on anything about that?
So I don't know. The good and bad of the Bayesian approach is that can be implemented. It's a computational model. It's not a neural model, so it can be implemented, and it could be consistent to different neural possibilities. One that works is duration channels, right? So if you have kind of duration channel, what is the prior? Well, the prior would be a pre-activation of the duration channels. So kind of work. You would have to time it as well. So you would have, like, you need some sort of rhythmic activation in addition to the duration channels, but it's possible. So that points to something like an oscillator or a multiple, like a two neuron interaction, right? but it's possible. So you would have an array of neurons with different delays. So and each represent the duration and the timing. So it's a
So
congruent
we've got some
duration
questions from
plus
people who are
time.
not me now, so I'll cut you off.
Okay.
Julia at Nottingham Trent.
Hi, sorry. Can you hear me?
No, yes.
Yeah, okay, cool. Thank you. Yeah, I have a question because I'm working also on kind of similar project, synchrony with augmented VR reality, but coming from a different background because I'm using dynamical systems or more oscillatory model where there is no prediction. It's only coupling. And I was wondering, because I came from a cognitive psychology background, now I'm working with movement science. And I don't know how to find a way to reconcile these two visions. Yeah, so yeah, I don't know what's your opinion on that.
So let me try to understand. So you're trying to synchronize to avatar or to things, and one of them reacts to the other. Is that what?
Yeah, but basically we're using the Kuramoto model or the Ashkabe model that came more from another literature, and there is no prediction in this model. No. So I'm always kind of arguing with my colleague or trying to, find a middle ground because coming from more cognitive psychology prediction Bayesian framework, it's hard to reconcile the two, basically.
So your question is similar to what Jonathan was saying. Like, how do you reconcile this with higher level regularity? One of them in music, which is very simple, is accelerando. Right, a lot of pieces, they have a slight tendency to increase speed. So is that a forward model? Right, is that a kind of prediction based on the on something you are doing? Like, can you predict when the next one, when the next movement is, because you are accelerating, you are running faster and faster. So acceleration are difficult to measure because it's second order properties, but you could try to look into basically inducing an accelerating state, if that makes sense. So Jonathan, I think you were, did you want to answer the question too?
Yeah, well, I'm just excited. I need to talk with you guys later. I've got trying to bring together oscillators and Bayesian models, and yeah, so we'll talk in a bit.
Could be very interesting.
I'll follow
thank you.
And Anne?
Yes. Hello. Thanks a lot. I was just curious as to what kind of stimuli you actually used, both in the auditory and the visual modality. What kind of rise time, duration, beeps, clicks?
Yeah, we tried different things. So in different experiments might not be exactly the same, but I think they were on ramp, off ramp, like maybe 20-30 milliseconds beeps. We've tried different frequencies. In the music experiment, of course, we use something a little bit more like MIDI. Sounds. I mean, I think it's still sound sine wave, but it's so very simple. We have tried clicks, and I didn't find a big difference in the general pattern. I think that Darren has tried decaying sinusoids and kind of sweeps. Again, the general model is the same, but the likelihood changes shape a lot. So the prior would also change shape. So yeah, so having like stimuli that increase in amplitude, for example, over time would change your likelihood, of course. And we have attempted something, but it's a little bit more complicated.
Yeah.
It doesn't capture it completely,
I don't know if we have more time. It's probably the end.
No reason we can't stay on and ask a few more questions. But I'll turn it over to Elmira first, since she hasn't spoken yet.
Sorry, I have to also leave quickly, so I ask a quick question about the Bayesian model that you were showing. I do remember in some of the plots I saw that the posterior was developing into something bimodal from the likelihood and the prior, which I was wondering how you're implementing the model. It's not like a updating, it's like Monte Carlo, or?
No, so in the models there are in continuous time. So we have continuous distribution. It goes back to, what is, I know it's a very it's a simplification. I would say to have it in real time of the use of particle filter.
Okay. So you're basically using a dynamic filter,
so
not
in the
like sequential updating.
So okay, so especially in the tapping literature, like in the tapping example, you could have a model with just like a discrete model with each of the tapping. So that is one possibility. But we are trying to develop a continuous model that has some of the features of the discrete one. So it's basically hybrid in between a continuous and a discrete, which is applying particle filters. So you have multiple dynamic that sample the probability distribution.
Okay. So you sample the probability distributions and then you update.
Yes.
Okay, I see.
So we have implemented a version with the Kalman filter as well to see if it works. We have had a little bit of problem with the noise, with the correlation. So the covariance matrix is so because the noise is correlating, we need to work out with the covariance matrix. So there is a bit of problem with the stability of the system. But yeah, it's I hope that we have a colleague, a collaborator, Hugo from Brazil that is working. So he's a mathematician. He's working at it. It's more complex than I can handle. But basically, because the noise in the system is correlated, the system itself needs to have some specific correlation, like a covariance matrix.
And what is your assumption about the weighting of the prior and the likelihood at each timestamp?
So in the models that I presented with perception, there is no weighting. We only have one parameter that is a forgetting factor, which is just an added constant, which allows you to forget. But otherwise, the weighting is just in relation to the shape of the distribution minus this constant on the prior.
And the forgetting has a cutoff after, for example, 3, 4 sample.
Yeah. So what we do, it's a little bit more. So we just add a kind of a probability so that if you don't present any stimulus, the probability just flattens out. But it's another,
something continuous.
It's basically it's a mixture of the prior is a mixture between a flat and this kind of distorted Gaussian, and the weighting is between the two priors, if it makes sense.
I see. Okay, thank you so much.
All right, and we're quite over time, but I'd be happy to let if Anne is still around, if you wanted to ask. Oh no, she's not. Okay, well, Max, thank you so much for joining us, and I'm going to follow up with you guys soon. But everyone, I hope you'll join us again for January TRF. Information coming soon. Bye-bye.
Thank you very much. Thank you, everybody.